Right now, as you watch this, you are standing on the edge of everything we can ever know. 46.5 billion light-years away from where you sit, there exists a boundary. Not a wall, not a barrier you could touch. That's something far more absolute, a horizon beyond which no information can ever reach us. No light, no signal, no evidence that anything exists at all. This is the edge of the observable universe, and what makes it terrifying isn't what's there. It's what it reveals about the nature of reality itself. For the next 90 minutes, we're going to undertake a journey to that edge. We'll examine 3 possibilities for what the universe truly is. Each one supported by evidence, each one unsettling in its own way. And by the end, you lines understand why the question "does the universe have an edge" might be the wrong question entirely. Because the answer, as we'll discover, depends on something far stranger, the shape of space itself. This is a story about geometry, light, and the absolute limits of human knowledge. This is the story of the edge. Let's start with something you probably learned in school. Nothing travels faster than light. 186,000 miles per second. 300,000 kilometers per second. This isn't just a speed limit for particles. It's a fundamental constraint on cause and effect. On information itself, light doesn't just illuminate the universe. It defines what universe we can observe. The universe is 13.8 billion years old. We know this with remarkable precision, thanks to measurements of the cosmic microwave background, the abundance of light elements, and the expansion rate of space. 13.8 billion years since the Big Bang. So here's the logical conclusion. If the universe is 13.8 billion years old and light is the fastest thing in existence, then we should be able to see out to a distance of 13.8 billion light-years in every direction. Right, wrong, we can see much, much farther. The most distant objects we observe are over 46 billion light-years away. The diameter of the observable universe is 93 billion light-years across. This shouldn't be possible. This appears to violate everything we just said about the speed of light, but it doesn't. And understanding why this isn't a contradiction is the first step to understanding what an edge of the universe actually means. The key is this: space itself can expand faster than light, not objects moving through space. That's still limited. But the fabric of space itself, stretching, growing, carrying galaxies along with it like boats on an expanding ocean. When light left the most distant galaxies we can see, those galaxies were much closer to us. But over the 13.8 billion years that light has been traveling, space itself has been expanding. The galaxy that emitted that light has been carried away from us by expansion. By the time the light reaches us, that galaxy is now over 46 billion light-years distant. But there's another barrier, one that's even more fundamental. In the beginning, the universe wasn't transparent. For the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. Photons couldn't travel freely. They'd scatter off charged particles almost immediately, like trying to see through a thick fog. Light couldn't propagate. Then, 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. Suddenly, the universe became transparent. Light could travel freely for the first time. That moment, that transition, is what we call the cosmic microwave background. The CMB. It's the oldest light in the universe. The light from that moment has been traveling toward us ever since, redshifted by expansion from visible light into microwaves. And here's the crucial point. We cannot see past the CMB. It's not that there's nothing there, it's that the universe was opaque before that moment. The CMB is like a wall of fog surrounding us in every direction, 46.5 billion light-years away. This is our cosmic horizon, the edge of the observable universe. Not because there's nothing beyond it, but because we cannot receive information from beyond it, ever. This is the first edge, the observational edge. The limit of what light allows us to know. But is this the edge of the universe itself, or just the edge of what we can see? To answer that, we need to understand what happened to space during those first fractions of a second. We need to understand expansion itself. Here's a question that sounds absurd. What shape is the universe? Not what shape do galaxies form? Not what shape is the Milky Way, but what is the geometric shape of space itself? This question would have seemed meaningless before Einstein. Space was just an empty stage where physics happened. But Einstein's general relativity revealed something profound. Space isn't just a backdrop. It's a dynamic, curved entity, mass and energy curve space. And the curvature of space determines how objects move. On cosmic scales, the curvature of space determines the ultimate fate and size of the universe. There are three possibilities. First, flat space. This is the Euclidean geometry you learned in school. Parallel lines never meet. The angles of a triangle add up to exactly 180 degrees. Flat space extends infinitely in all directions. If the universe is flat, it's infinite. Second, positively curved space. Imagine the two-dimensional surface of a sphere, like Earth's surface. This is a space with positive curvature. On a sphere, parallel lines eventually meet. The angles of a triangle add up to more than 180 degrees. And crucially, a positively curved space is finite. It has a finite volume, but it has no edge. You can travel in any direction forever and never reach a boundary, just like walking around Earth's surface. Third, negatively curved space. This is hyperbolic geometry, saddle-shaped. In this space, parallel lines diverge. The angles of a triangle add up to less than 180 degrees. Negatively curved space is infinite, like flat space, but it expands even faster. So which is it? What's the shape of our universe? We measure this using something called the density parameter, omega. This compares the actual density of the universe to the critical density, the density needed for flat space. If omega equals 1, space is flat. If omega is greater than 1, space is positively curved, closed, finite. If omega is less than 1, space is negatively curved, open, infinite. For decades, cosmologists worked to measure omega. They studied galaxy clusters, they measured the Hubble constant. They analyzed the cosmic microwave background. In 2001, the Wilkinson Microwave Anisotropy Probe, WMAP, gave us our first precise measurement. The WMAP spacecraft measured tiny temperature fluctuations in the CMB, fluctuations that encode information about the geometry of space. Then, in 2013, the Planck satellite provided even better data. Higher resolution, more precision. The result? Omega equals 1.00, plus or minus 0.02. Within the margin of error, the universe is perfectly flat. But here's the thing about that margin of error. We can't prove the universe is exactly flat. We can only say it's flat to within 2%. And that small uncertainty leaves room for either curvature, but the data strongly suggests flatness. And if the universe is flat, then mathematically, it's infinite. An infinite universe, let that sink in for a moment. Not just really big, infinite, going on forever in every direction. Containing infinite matter, infinite galaxies, infinite stars. This is the first scenario, the infinite plane. And it comes with implications that are both awe-inspiring and deeply unsettling. If the universe is flat, if it's truly infinite, then we need to confront what infinity actually means. Infinity isn't just a really big number, it's a fundamentally different concept. In mathematics, infinity leads to paradoxes and strange results. In physics, infinity often signals that something's wrong with our theories. But if the universe is infinite, those infinities are real. Consider this. The observable universe contains approximately 2 trillion galaxies. That's A2 followed by 12 zeros. Each galaxy contains hundreds of billions of stars. The total number of stars in the observable universe is roughly 10 to the 24th power. A 1 followed by 24 zeros, that's what we can see. That's within our 46.5 billion light-year radius. But if the universe is infinite, then beyond our cosmic horizon, there are infinitely many more galaxies. Infinitely many more stars, infinitely many more planets. The cosmological principle tells us that the universe is homogeneous and isotropic on large scales. It looks roughly the same everywhere. The same density, the same distribution of galaxies, the same physical laws. If that principle holds everywhere in an infinite universe, then probability becomes certainty. Here's why. The observable universe contains a finite number of particles, a finite volume. The number of possible arrangements of those particles is vast, but finite. It's roughly 10 to the power of 10 to the 120. But if the universe is infinite, then there are infinitely many regions of space the same size as our observable universe. And if there are infinitely many regions, then every possible arrangement of particles must occur, not just once, infinitely many times. This leads to an unsettling conclusion. There are infinite copies of you. Not similar people, not people who look like you, but exact duplicates. People with the same atomic arrangement, the same memories, the same thoughts you're having right now. In an infinite universe, there's a region of space, unimaginably far away, where every atom is arranged exactly as it is here. Where someone identical to you is watching a video identical to this one. Where Earth's history played out exactly the same way. And not just one such region, infinitely many. This isn't science fiction. This is a mathematical consequence of infinity plus homogeneity. It's called the quantum recurrence theorem, though that's a bit of a misnomer. It's really just combinatorics applied to cosmology. Of course, these duplicate regions would be staggeringly far away. The distance to the nearest identical region would be roughly 10 to the power of 10 to the 118 meters. That's a 1 followed by 10 to the 118 zeros. A number so large, it's meaningless to human intuition. You could never reach these regions, you could never communicate with your duplicates. The expansion of space makes them forever inaccessible. But they would exist. In an infinite universe, they must exist. Some find this comforting, a form of immortality. Somewhere, infinitely many versions of you continue on. Others find it deeply disturbing, a loss of uniqueness, of meaning. But there's a deeper problem with infinity. Can we ever prove the universe is infinite? Can we ever be certain? No. We can only observe our finite cosmic horizon. Everything beyond that is inference, theory. We can measure that space is flat to within our precision. But we can never measure infinite flatness, we can never confirm infinite extent. The universe could be flat within our observable region and yet finite. It could be so large that its curvature is undetectable to us, but still closed. Finite but so vast that it appears flat. This is one of the fundamental limitations of cosmology. We can only observe a finite patch, we can never see the whole. And there's another issue, inflation. In the early universe, during the first fraction of a second, space underwent exponential expansion, cosmic inflation. During inflation, space expanded so rapidly that regions that were once in causal contact were driven far apart, beyond each other's horizons. Inflation predicts that space should be very, very flat. Any initial curvature would be smoothed out by the rapid expansion. This is called the flatness problem, and inflation solves it. But inflation also means that the universe could be much, much larger than the observable region. Even if the universe is finite, it could be so vast that we see only a tiny flat patch of a much larger, possibly closed universe, so we're left with uncertainty. The data suggests flatness, flatness suggests infinity. But we can never be certain. This is scenario 1. An infinite universe, flat geometry, extending forever in all directions. No edge, no boundary, just space and matter, continuing without end. It's consistent with observations. It's supported by theory, and it's deeply strange. But there are other possibilities. What if the universe is finite, not finite in the sense that it has an edge you could fly to, but finite in the sense that it has a fixed, finite volume. Finite but without boundary. This is the closed universe. A universe with positive curvature. To understand this, we need to think in analogies. Imagine living on the surface of a sphere, a two-dimensional being on Earth's surface. You can walk in any direction, you never encounter an edge. But the surface is finite, it has a finite area. If you walk far enough in one direction, you'll eventually return to where you started. The surface of a sphere is two-dimensional but curved into a third dimension. It's finite but has no boundary. Now extend this up one dimension. A three-dimensional space curved into a fourth dimension. A hypersphere, a three-sphere, technically. This space has finite volume, but no boundary. You could fly a spaceship in any direction and eventually, if you went far enough, return to your starting point from the opposite direction. This is what a positively curved, closed universe would be like. In the early days of cosmology, Before precision measurements, a closed universe was considered quite plausible. Some measurements suggested omega was greater than 1. The density seemed high enough. But as data improved, the evidence shifted toward flatness. Today, the Planck data gives us omega equals 1.00 plus or minus 0.02. This makes a closed universe unlikely, but not impossible. If omega is actually 1.02, just at the edge of the error bars, the universe could be closed. What would that mean? First, it means the universe has finite volume. We could, in principle, calculate how much space exists. It would be vast, far larger than the observable universe, but finite. Second, it means the universe is topologically a three-sphere. If you could somehow travel far enough, faster than the expansion of space, you'd return to your starting point. Not that anyone could actually do this. The distances involved and the expansion rate make it practically impossible. But in principle, the universe would wrap around on itself. Third, it has implications for the fate of the universe. In a closed universe with enough density, gravity could eventually overcome the expansion. The universe would reach a maximum size, then begin to contract, the big crunch. All of space collapsing back down, temperatures rising, galaxies merging, until everything ends in a singularity. However, this assumes no dark energy. With dark energy, even a closed universe could expand forever. The accelerating expansion might overcome the curvature. We'd still have heat death, just in a finite space rather than infinite space. There's something aesthetically appealing about a closed universe. It's finite, comprehensible in a way infinity isn't. It has a definite size, a definite amount of matter. But it's also unsettling. We're trapped, enclosed, in an infinite universe. There's always more. In a closed universe, this is all there is. A finite bubble of space, expanding into ... what? That's the problem with the closed universe. If space is finite, what's outside it? The answer, according to general relativity, is nothing, not empty space, literally nothing. Space itself is finite. There is no outside. This is hard to visualize. We're used to thinking of objects being inside space. But space isn't inside anything. If space is finite, it's just finite. The question what's outside is meaningless. It's like asking what's north of the North Pole. The question assumes a framework that doesn't exist. Still, it's an uncomfortable answer. And there's a practical issue. How would we know if the universe is closed? If the curvature is very slight, if the universe is so large that it appears flat within our observable region, we might never detect the curvature. We'd need to observe over scales much larger than our cosmic horizon to see the effects. Some cosmologists have looked for signs of closure. One signature would be a repeating pattern in the CMB. If the universe is closed and smaller than our horizon, we might see the same structures repeated, the same temperature fluctuations, because we're seeing around the universe. So far, no such patterns have been found. Another approach is to look for the topology. Even if space is flat locally, it could have a non-trivial global topology. The universe could be shaped like a three-dimensional torus, for example. Flat locally but wrapping around, finite but without curvature. Again, searches have come up empty. Within the observable universe, space appears flat and simply connected, but the possibility remains. The universe could be closed, finite, bounded in volume but not in the sense of having an edge. A hypersphere of space, vast beyond comprehension, but ultimately limited. This is scenario 2, a finite universe, positive curvature, closing in on itself. No edge you could reach, but a finite total space. It's less favored by current data, but not ruled out. And then there's the third possibility, the strangest one. To understand the third scenario, we need to go back to the beginning. Not the Big Bang itself, but the first trillionth of a trillionth of a trillionth of a second after it. This is the era of cosmic inflation. In 1980, a physicist named Alan Guth proposed a radical solution to several problems in cosmology. The horizon problem, the flatness problem, the monopole problem. His solution: in the earliest moments after the Big Bang, space expanded exponentially. Not just fast, exponentially, doubling in size at incredibly short intervals. During inflation, which lasted from about 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26. That's 100 trillion times larger. In a tiny fraction of a second, a region of space smaller than an atom expanded to larger than the observable universe today. This rapid expansion solves several problems. It explains why the universe looks the same in all directions even though regions on opposite sides of the sky were never in causal contact. During inflation, they were in contact, then pushed apart faster than light. It explains why space is so flat. Any initial curvature gets stretched out by inflation, like wrinkles on a balloon being inflated. And it explains why we don't see certain exotic particles predicted by grand unified theories. They were diluted to unattackable densities by inflation. But inflation does something else. It tells us that the observable universe is just a tiny patch of a much larger space. Think about it. During inflation, space expanded by an enormous factor. The region that became our observable universe was once much smaller. But the regions outside our observable universe also inflated. They're still out there, beyond our horizon, containing their own galaxies, their own structures. How much larger is the total universe compared to the observable region? It depends on the details of inflation. How long it lasted, how fast space expanded. Different models give different answers. Some estimates suggest the universe is at least 250 times larger in radius than the observable universe. That would make it 15 trillion light-years across, vast, but still finite. Other models, depending on how long inflation lasted, suggest the universe could be 10 to the 23rd times larger than the observable region. A number so large is effectively infinite for any practical purpose, and some versions of inflation, called eternal inflation, suggest the universe is actually infinite. Here's how eternal inflation works. Inflation is driven by a field called the inflaton field. This field has energy, and that energy causes space to expand. Eventually, the inflaton field decays, inflation ends, and the energy goes into creating matter and radiation. That's the Big Bang transition. But quantum mechanics tells us that fields fluctuate. The inflaton field has quantum jitters. In most regions, the field decays and inflation ends. But in some regions, quantum fluctuations push the field back up. Inflation continues there. Those regions keep inflating, and within them, new regions stop inflating while others continue. It's a fractal process. Inflation never truly ends globally. It only ends in local patches. Each patch where inflation ends becomes a universe like ours. A pocket universe, a bubble, and there are infinitely many such bubbles. This is eternal inflation, a theory where the Big Bang wasn't a single event but an ongoing process. Our universe is one bubble in an infinitely inflating multiverse. The evidence for inflation is strong. The uniformity of the CMB, the flatness of space, the pattern of density fluctuations that seeded galaxy formation all match inflation's predictions incredibly well. But eternal inflation is more speculative. It's a consequence of some inflation models, but not all. And it makes a radical claim. Our universe isn't the universe, it's one among infinitely many. Each bubble universe would have its own Big Bang, its own history, and potentially, its own laws of physics. This brings us to the third scenario, the multiverse, and the question of what lies between universes. If eternal inflation is correct, then our universe has an edge. Not the edge of space itself, but the edge between our bubble and the eternally inflating space outside it. Or more precisely, the edge between our bubble and other bubbles. Imagine an infinite expanse of space, inflating exponentially. Within this space, bubbles form. Regions where inflation ends, where the inflaton field decays, where matter and radiation appear. Each bubble expands, but much more slowly, and the surrounding inflating space. The bubbles are separated by ever-expanding regions of inflating space. Each bubble is causally disconnected from the others. Light cannot travel between them. They can never communicate. They are, for all practical purposes, separate universes. This is the multiverse, not science fiction. A serious proposal emerging from our best theory of the early universe, and it gets stranger. String theory, our leading candidate for a theory of quantum gravity, predicts something called the landscape. The mathematical structure of string theory allows for an enormous number of possible vacuum states, different configurations of extra dimensions, different values for physical constants, different particle physics. The number of possible states is estimated at 10 to the 500th power. a 1 followed by 500 zeros. Each bubble universe in eternal inflation could realize a different vacuum state, a different set of physical laws. In one universe, the electron mass might be different. In another, the strength of gravity might be stronger. In another, there might be additional forces we don't have. Or fewer forces, different numbers of dimensions of space. Most of these universes would be sterile, inhospitable to life. In some, atoms couldn't form. In others, stars couldn't ignite. In others, galaxies couldn't coalesce. But in a tiny fraction, the laws of physics would be just right for complexity. For chemistry, for life, this is the anthropic principle applied to the multiverse. We find ourselves a universe with light-permitting laws not because those laws are special or designed, but because we could only exist in such a universe. We're selected by our own existence. It's a controversial idea. Some physicists embrace it. Others find it untestable and therefore unscientific. But it leads to a profound question. What exists at the boundary between universes? According to eternal inflation, the space between bubbles is still inflating. It's expanding exponentially. Any two bubbles are being driven apart faster than light. They can never collide. They can never interact. So the edge of our universe is an expanding wall of inflating space. A region where the M-flattened field hasn't decayed yet. Where space is still undergoing exponential expansion. We could never reach it. As we tried to approach it, space would expand faster than we could travel. It's like trying to swim to a receding shore in a current that moves faster than you can swim. But what if two bubbles did collide? What if, in the early universe, before they were driven too far apart, two bubble universes touched? This would leave a signature, a disk-shaped region, in our CMB where temperatures and densities are anomalous. Cosmologists have searched for such signatures. There are a few anomalies in the CMB, like the cold spot, but none that definitively indicate a bubble collision. If bubbles can collide, then in principle, we could detect another universe. We could find evidence of the multiverse. But even if we did, we could never visit it. We could never communicate with it. The bubble collision would have happened in the early universe, and by now, that other universe would be unreachably far away, receding faster than light. So we're left with a strange picture. Our universe might be a bubble floating in an eternally inflating space, surrounded by infinitely many other bubbles, each with potentially different laws of physics, and all forever beyond our reach. This is the edge in scenario 3, not an edge of space, but an edge of our reality. A boundary beyond which our laws of physics might not apply. A wall of inflating space we can never cross. It's isolating. We're alone. Not just alone in our universe, but alone among infinitely many universes we can never contact. Some find this idea liberating. It explains the apparent fine-tuning of our universe's laws. It removes the need for a designer. Others find it scientifically troubling. If we're just one universe among infinitely many with different laws, then we lose predictive power. Anything becomes possible somewhere. How do we test theories? And there's a philosophical objection. If there are infinitely many universes, each with its own set of laws, have we really explained anything? We've just pushed the mystery one level up. Why does the multiverse exist? Why these particular rules for eternal inflation and string theory? The multiverse doesn't answer ultimate questions, it just reframes them. That the evidence for inflation is strong, and eternal inflation is a natural consequence of quantum inflation. And string theory, for all its challenges, remains our best hope for unifying gravity and quantum mechanics. So scenario 3, the multiverse, remains a serious possibility. Our universe as a bubble with a boundary made of eternally inflating space, causally disconnected from infinitely many other bubbles. An edge we can never reach, a boundary that isolates us in our own reality. We've explored 3 scenarios. An infinite flat universe, a finite closed universe, a bubble universe within an eternal multiverse. Each is consistent with current observations, each has evidence supporting it. And each has a different answer to the question, does the universe have an edge? But underlying all 3 scenarios is a deeper truth, a more unsettling reality. There are things we can never know. This isn't a failure of science, it's not a limitation of our technology or our intelligence. It's a fundamental feature of the universe we inhabit. Let's consider the particle horizon. This is the boundary of the observable universe, the most distant point from which light has had time to reach us. Currently, It's at 46.5 billion light-years. Beyond this horizon, galaxies exist. We're confident of this. The universe doesn't stop at the edge of our vision. But we cannot observe those galaxies, not yet. Light from them hasn't had time to reach us. In principle, as time passes, our particle horizon expands. We should be able to see farther. More of the universe should come into view. But there's a complication: the cosmic event horizon. This is the boundary beyond which light emitted today will never reach us, no matter how long we wait. Because of the accelerating expansion-driven, dark energy, space is expanding faster than light can cross it for sufficiently distant regions. The cosmic event horizon is currently about 16 billion light-years away. It's shrinking every moment. Galaxies cross this boundary and become forever unobservable. In the far future, trillions of years from now, only the local group of gravitationally bound galaxies will be visible. Everything else will have receded beyond the event horizon. Future astronomers will look out into the night sky and see only a handful of galaxies. They'll have no evidence that billions of other galaxies once existed. They'll be observationally isolated, and there's nothing we can do about this. It's a consequence of dark energy, of accelerating expansion. Information is being lost to us permanently. This is the first limit. The causal limit. Beyond the event horizon, we cannot affect or be affected. Events that are outside our light cone, causally disconnected. But there's a second limit, the quantum limit. At the smallest scales, quantum mechanics tells us that information is fundamentally uncertain. The Heisenberg uncertainty principle limits what we can know about particles. We cannot simultaneously know position and momentum with arbitrary precision. On cosmological scales, quantum fluctuations in the inflated field during inflation seeded the density variations that became galaxies. Those fluctuations were quantum, probabilistic, intrinsically uncertain. This means the large-scale structure of the universe has an irreducible randomness built into it. We cannot predict exactly where galaxies formed. We can only give probabilities. And if eternal inflation is correct, quantum fluctuations determine which regions stop inflating and which continue. The multiverse, if it exists, is shaped by quantum randomness. There's a third limit, the mathematical limit. In 1931, a mathematician named Kurt Dell proved an astonishing theorem. In any consistent mathematical system complex enough to include arithmetic, there are true statements that cannot be proven within that system. This is Gödel's incompleteness theorem. It shows that mathematics itself has limits. There are mathematical truths we can never prove. Some cosmologists have argued that Gödel's theorem applies to cosmology. If the universe is mathematical, if the laws of physics are mathematical structures, then there may be truths about the universe that cannot be proven from within the universe. We are observers within the system. We cannot step outside to see the whole. This limits what we can know. And finally, there's the observational limit. We can only measure what we can interact with. We can only observe what sends us signals. The observable universe, by definition, is all we can observe. If the universe is infinite, we can never confirm it. We can only measure a finite patch. If the universe is closed but larger than our horizon, we might never detect the curvature. If the multiverse exists, but other bubbles are causally disconnected, we can never observe them. Our knowledge is fundamentally limited to our cosmic horizon. Everything beyond is inference, theory, speculation. This is uncomfortable. We want certainty. We want answers. But the universe doesn't owe us answers. And some questions might not have answers we can access. Does the universe have an edge? We've seen 3 possibilities. But we may never know which is correct. Is the universe infinite? We can't observe infinity. We can only measure that it's very, very flat. Is the universe closed? If it's larger than our horizon, we might never detect the curvature. Is the multiverse real? If other bubbles are forever beyond our reach, we can't observe them. These aren't failures of science, they're honest acknowledgments of science's limits. And yet, there's something profound in this uncertainty. We live in an age where we can measure the universe to incredible precision. We know its age to within tens of millions of years. We know its composition to within a few percent. We know the laws of physics that govern it, but we also know what we don't know. And we know some things we may never know. That's not weakness, that's wisdom. Science isn't about having all the answers. It's about asking the right questions and being honest about the limits of our knowledge. The edge of the universe, whether it's an observational horizon, a causal boundary, or a multiverse wall, represents the edge of what we can know. And that edge is as much a part of reality as anything we can observe. In the end, perhaps the most terrifying thing about the universe's edge isn't what's beyond it. It's the realization that there are fundamental limits to human knowledge, that some truths might be forever beyond our reach. And yet, we continue to look, we continue to measure, we continue to ask. Because even if we can never see beyond the horizon, the act of reaching toward it defines us. We began this journey at the edge of everything we can know. 46.5 billion light-years away, where the cosmic microwave background marks the limit of our vision, we've explored what might lie beyond. An infinite expanse, a closed hypersphere, a multiverse of bubble universes. Each scenario has evidence. Each is possible, none is certain, and that uncertainty, that unknowing, is part of what makes us human. For 13.8 billion years, the universe evolved without observers. Stars formed and died, galaxies collided and merged. Space expanded, and nobody watched. Then, on one small planet orbiting an ordinary star in an unremarkable galaxy, something extraordinary happened. Matter became conscious. The universe developed the ability to observe itself. We are that, you are that, collections of atoms pondering the nature of space and time. We've built telescopes that can see across billions of light-years. We've developed mathematics that can describe the curvature of space itself. We've sent probes to the edge of our solar system and gazed at the cosmic microwave background from the beginning of time. And all of it, all of this knowledge, all of this understanding, exists within a finite cosmic horizon. A bubble of observability in a potentially infinite universe. But within that bubble, we've achieved something remarkable. We've mapped our place in space and time. We've understood the laws that govern reality. We've faced the limits of what we can know and continued to push against them. The universe may be infinite, with no edge in sight. Or it may be finite, curved back on itself in ways we can't perceive. Or it may be one bubble in an infinite multiverse, forever isolated from other realities. We may never know which. But we will keep looking, we will keep measuring. We will keep asking questions, even questions that might not have answers. Because the edge isn't just a place, it's a challenge. A reminder that the universe is stranger and more wonderful than we imagined. An invitation to keep exploring, keep wondering, keep reaching toward what we cannot yet see. Perhaps, in the end, the edge isn't something to find, it's something to push against. A horizon that recedes as we approach, always revealing new mysteries, new questions, new frontiers. We stand at the edge of everything we can know. And from here, we look outward, into the unknown, and ask, what's next? The universe may be indifferent to our questions, but we ask them anyway, because we are the universe trying to understand itself. And that might be the most extraordinary thing of all. Thank you for joining me on this journey to the edge. If this changed how you see your place in the cosmos, if it made you think, if it filled you with wonder or terror or both, share it with someone. Let them stand at the edge with us. And if you want to explore more mysteries at the frontiers of knowledge, subscribe, because there are more edges to find, more boundaries to examine, more questions that need asking. The journey continues, the edge awaits.